Welcome everyone, and thank you for tuning into this insightful session. Whether you are someone with a passion for data science, a student taking your first steps into machine learning, or a professional looking to level up your skills, you've landed in the right spot. In today's video, we're about to unravel the magic behind one of the most powerful and widely applied algorithms in machine learning, support vector machines. We'll explore its ability to classify and regress data, how it works with different kernels, and how you can apply this algorithm to real-world problems. This algorithm is used in text classification, image recognition, and even bioinformatics for tasks like protein classification. By the end of this video, you'll have a solid understanding of how SVM works, both theoretically and practically. We'll also look at how to tune hyperparameters, choose the right kernel, and evaluate the performance of SVM models. So stay tuned. Let's start with the basics. What exactly is support vector machines? SVM is a supervised machine learning algorithm that is used for classification and regression tasks, but its most popular application is in classification. At the core, SVM tries to find the best decision boundary, also called as hyperplane, that separates different classes of data points. Think of this boundary as a line or surface that divides the two categories, such as spam versus non-spam emails or disease versus healthy individuals in medical datasets. But SVM doesn't just place any boundary. It looks at the one that maximizes the margin, the gap between the nearest data points, known as support vectors, and the decision boundary. This margin maximization leads to a better generalization of the model, making it more robust when a new unseen data comes along. SVM is very powerful because it can handle both linearly separable data, where you can draw a straight line to separate classes, and non-linearly separable data, where classes can't be separated by a straight line. Now let's focus on support vector classifiers, which is a special case of SVM designed for classification problems. SVC finds the optimal hyperplane or decision boundary that best separates the data points into different classes. But how does it do that? Here's where support vectors comes into play. These are the data points that are closest to the decision boundary. In the context of SVC, only the support vectors influence the position and orientation of the hyperplane, not the rest of the data points. This makes SVM a slightly efficient algorithm, as we don't have to consider every data point in the dataset when training the model. The SVC algorithm is like a balancing act. It wants to maximize the margin between the classes but also minimize classification. In SVM, there are two types of decision boundaries you might encounter: hard margin and soft margin. The hard margin approach is strict and tries to perfectly separate the two classes with no errors allowed. However, this works only when the data is linearly separable, meaning you can perfectly divide the classes with a straight line or plane. But in the real world, data is often noisy and you can't always perfectly separate the classes. The soft margin approach allows for some misclassification, balancing between the width of the margin and the number of errors allowed. This is achieved by introducing a slack variable denoted by epsilon I xi to handle the misclassification. In practice, the soft margin is often more useful, as it helps to model generalize better to new data by not overfitting the training data. Think of it as being tolerant to small errors, while still trying to maintain a good boundary. Let's dive into mathematics behind the SVC model. Don't worry, we'll keep it intuitive. The goal of SVC is to maximize the margin between the classes. In mathematical terms, this means we are trying to minimize the norm of the weight vector W while ensuring that all data points are correctly classified. The optimization function for SVC can be written as minimum of 1 by 2 norm of W whole square, which is subject to the constraints y bracket vector W transpose xi plus b bracket close greater than equal to 1 for all I points, where W is the weight vector that defines the hyperplane, xi is the ith data point, yi is the class label, which can be denoted by +1 or -1, and b is the bias term. The margin is essentially distance between the hyperplane and the closest data points. The optimization problem ensures that the distance between the hyperplane and the support vectors is maximized, which leads to a more generalizable model. Let us talk about the cost function that are used to train the SVM. The hinge loss penalizes points that are either misclassified or fall within the margin. Objective function that SVM optimizes is minimum of 1 by 2 norm of W whole square plus C from I as a summation from I equal to 1 to n epsilon I, where C summation I equal to 1 to n epsilon is the hinge loss. Epsilon I is the distance of the incorrect data points from the margin plane. C is the regularization parameter that controls the trade-off between maximizing the margin and minimizing misclassification. That is, how many points do we need to avoid misclassification. This cost function ensures that points that are correctly classified and lie outside the margin do not contribute to the loss, which allows for wider margin. The parameter C gives you control over the flexibility of the model. Higher C value prioritizes fewer misclassification, while lower C values prioritizes a wider margin. Let us now move from classification to regression with the support vector regressor. While SVC focuses on finding decision boundary, SVR focuses on fitting a line or hyperplane that minimizes the errors in predicting continuous values. The key difference is that SVR allows for small deviations, that is, it tries to fit the data within an epsilon insensitive tube, ignoring errors that fall within a certain threshold, epsilon. So instead of penalizing every error, SVR only cares about the points that lie outside the tube. This makes SVR more robust to outliers and small fluctuations in the data. The cost function used in SVR is slightly different from SVC, as it uses epsilon insensitive loss. If a point falls inside epsilon margin, it does not contribute to the loss, but if it is outside the tube, it is penalized. The optimization function of SVR is minimum 1 by 2 norm of W whole square plus C is a summation from I equal to 1 to n epsilon I, where eta is the distance between the points above the marginal planes or error above margin, and C controls the trade-off between fitting the data and minimizing deviations. Now let us talk about the concept of kernels in SVM. Kernels are the key to making SVM work in high-dimensional or non-linear spaces. The basic idea is that data that isn't linearly separable in its original space can be transformed into a high-dimensional space where it is easier to separate. SVM uses the kernel trick, which allows us to compute the decision boundary in the higher dimensional space without explicitly transforming the data. This makes the algorithm computationally efficient. The RBF kernel is probably the most widely used kernel in practice. It uses Gaussian function to measure the similarity between the 2 points based on the distance in the feature space. The RBF kernel is flexible and can adapt to complex data shapes, making it one of the best choices for many real-world applications. One of the most common kernels is the polynomial kernel. This kernel works by mapping the data into higher dimensions using a polynomial function, which allows it to model non-linear relationships. The degree of the polynomial kernel determines the complexity of the decision boundary. Higher the degrees create more complex decision boundaries, while lower degrees might underfit the data. Lastly, we have the sigmoid kernel, which is based on the hyperbolic tangent or tanh function. This kernel is similar to the activation function used in neural networks. It's typically used for binary classification, but is not as widely used as the RBF or polynomial kernels. However, it can be useful in some specialized tasks. To recap, SVMs are incredibly versatile and can handle both classification and regression tasks. SVC maximizes the margin between classes using hinge laws and support vectors. SVR is ideal for regression problems and uses an epsilon insensitive loss to handle small deviations. Kernels extend SVM to nonlinear decision boundaries, with the RBF kernel being one of the most popular choices. Thank you for watching this detailed guide on support vector machines. I hope you now have a deeper understanding of how SVM works and how you can apply them to solve real-world problems. If you have any questions or need clarification, feel free to ask in the comments. And don't forget to connect with me on LinkedIn and subscribe to my YouTube channel for more exciting updates. Happy learning!